Alternative to running buses, which is lots of wires in parallel, is to do serial communications. And in serial communications, you send one bit at a time. Now, if you're sending one bit at a time, you have to figure out when those bits start, so you need to figure out what the clock is, because we're not sending a clock the way we did with the bus. Serial communications is also point-to-point. That is, it's not shared. So if we want to communicate with two different devices, we need two different serial communication links. But we can run much faster than buses, and the reason is we don't have to synchronize with all the wires. We don't have to worry about making sure all of our wires match up. The downsides of serial communications is much more complicated. As we mentioned, we have to figure out where the clock is, and we can do a whole bunch of other tricks to run much faster, including calibrating the wires and equalizing them. And serial communications are used wherever wires are long. And long is a definition that changes, because the faster you want to run your data, the longer a wire seems. So if you're doing very slow communications, you can use a very long wire. If you're doing very fast communications, you have to keep your wires short. So let's take a look at sending some serial data. Here I'm going to send the same data I had before, but I don't have a clock and I only have one wire, so I'm going to have to send one bit after each other. So you can see I send the control data first, then the address, then the data. So how are we going to actually transmit this? Well, we're going to transmit it in order. So the first bit's first and the last bit's last. And what is this going to look like? Well, we're going to have a signal that goes up and down over time. So instead of sending all of these bits at once, we're now sending them one after another. However, to understand this, we need to figure out the clock and figure out where to look. So the receiver has to know that these are where the bits are, so that it can look at that signal and get the data at the right time. And this is a tricky thing to do that we're not going to talk about in this class, but people know how to make this work. So serial communications can do something very clever to reject noise. So if we can use two wires and make the links much better, and the way we do that is by having one wire send our signal, transmit plus, and the other send the negative version of the signal, so transmit minus. At the end, we're going to subtract them to get back the original signal. And let's see why we do that. So here's our system. Here's the signal we want to send. So what we do is we send two versions of it, the negative version and the positive version. And then at the other end, we subtract them to get the data back. So why is this beneficial? Well, if there's an electrical noise in the middle, that noise is going to affect both wires. So here you can see that this red noise makes both of them go more positive, but when I subtract out the results, I also subtract out the noise. So why is this approach better? Well, it's better because when we subtract, we remove the noise. We have two wires, and if they're close together, whatever noise is coming from outside will affect them both the same way. When we subtract them, we get rid of that noise, and that gives us a stronger signal, which means we can make our data go faster. So let's take a look at how differential signaling works. So we're going to transmit two versions of our signal, plus and minus. And so here's the minus version. We've just multiplied everything by -1. Now I've got 0, -1, 0, -1 instead of 0, 1. This is an analog signal, so it's not really a digital signal. So we don't have to just have 0 and 1, we can use different voltages. At the end, we're going to subtract this. So now we go ahead and we create our signal and transmit it. Now let's take a look at what happens when we do the subtraction. So when we subtract them, we get back the original signal. In this case, we're going to get 0, 2, 0, 2, 0, 2, 2, because we're doing 1 minus -1, which is going to give us 2. So now we have our original signal. Now let's see what happens when we add noise to the signal. So say we have this noise spike in the middle of our signal. What does that do to our signals? Well, you can see how it's affecting both the transmit plus and the transmit minus. It's moving them up by half. How does this affect our final output? Well, if we look at what's happening here, it doesn't change anything. Because at this point here, instead of having 0 minus 0 to give us 0, we now have half minus a half, which still gives us 0. We've subtracted out that half that came from the noise. And the same thing happens here. Instead of having 1 minus -1 to give us 2, we get 1.5 minus -0.5, which also gives us 2. So by using the differential signals, we can take noise that affects both wires and subtract it out. And that gives us a cleaner signal, which allows us to run much faster. So what sort of I/O interfaces do we have today? Well, here's a layout for a modern processor chipset. And we can see that when we talk between the processor and the rest of the computer, we're using QPI if you're Intel or Hypertransport if you're AMD, and these are both point-to-point serial links. We have PCIe for talking to graphics cards, and this is again a point-to-point serial link. We have other connections such as SATA, which is also a point-to-point serial link. And then we have I/O connections for external devices such as USB and Ethernet, and USB is serial link, and Ethernet is also serial link, but they're not quite point-to-point. The memory is still sitting on a bus, but it's very limited. Usually we can only put 2 things on this bus because we don't want to slow it down too much. So, to sum up buses versus point-to-point serial links. Off-chip buses are going away because they're too slow. You've seen PCI go to PCIe, ATA go to serial ATA, etc. Why are they doing this? Well, data is too fast for long wires. The wire has capacitance, and because it has capacitance, it takes a long time to change the voltage. The longer the wire, the greater the capacitance, the longer it takes to change. It's also too hard to handle multiple devices on the same wire. So when you have multiple devices, you get more inductance, more capacitance, more resistance, and each additional device slows down the wires. And the real reason it's too hard to keep wires synchronized. Both of these other 2 issues, with wires being too long and wires being complex, means it's hard to keep the data in sync. And if we can't keep the data in sync, then we have to slow down the clock speed, and then the bus is slower. So the replacement, as we talked about, is serial communication, or SERDES. This stands for serial deserialization, and the idea here is we send 1 bit at a time. So there's no need to synchronize the wires because we're only sending 1 bit at a time. We figure out the clock as part of the signal. This is well known how to do, although it is tricky. But we do need to run much faster to get the same throughput. So if we're replacing a 32-bit bus with 32 wires with 1 serial link, that serial link has to run 32 times faster to send as much data. So the reason we can do this is because while they're more complex, we can afford the transistors. So we can afford to spend a lot of transistors to make a clever serial port instead of trying to figure out how to make a better wire. So we've said that off-chip buses are going away, and we're going to see the same thing in on-chip buses in the future. So when we start seeing 100 cores on a chip, we're also going to start seeing serial links on chips. The other thing that's important to keep in mind here, that while these transistors may be free, they also use a lot of power. So these serial ports use a lot of power on chips, so that part is not free.